Hello, everyone. My name is Ivan Arraut. I am a professor at the University of San Joseph and doctor in physics from Osaka University. This is a lesson recorded for the course of General Physics at the University of San Joseph for the Institute of Science and Environment. Physics of the 21st Century, Fundamental Aspects and Applications. The order of the talk is the following. I will mention what is unification, basic examples from all physics. I will mention Newton and the early physics, how did Newton got the ideas, Maxwell physics, which is basically the unification of electricity and magnetism, quantum mechanics plus special relativity, which is quantum field theory. But I will mention briefly what were the initial problems and other topics which you will see during the talk. First, what is unification in physics? All the physics, the modern physics, is focused on unification. What we're trying to do is to unify things which seems to be different are normally manifestations of this same phenomenon. An example is here, for example, on the left hand side, you will see the parabolic motion of a soccer ball versus the free fall of a person and the motion of the moon around the earth. These three phenomena are manifestation of the same phenomena, which is gravity. These three motions, basically. Gravity started early in the history with Galileo's free fall experiment. Galileo, when he threw two objects with different masses from the same height, he realized that those objects reached the Earth at the same time. Ideally, no, because of course, since there was air in between and there is friction with the air, there is a small deviation with the tendency of the heavier object to arrive first. But ideally, in vacuum, obviously the two objects will arrive at the same time. And this is a manifestation of what we call equivalence principle, which is the equality of the inertial mass and the gravitational mass. Gravitational mass is the source which makes the objects to fall to the air. Basically, mass times gravity, is the weight. But inertial mass is the mass which offers resistance to the change of motion. So when an object is pulled by gravity, it offers some resistance due to its mass. Incredibly, those two effects cancel each other and the motion is independent of the mass of the object. And this is what Galileo could find. For the case of Newton, for his formulation of gravity, he focused on the period of the moon. He knew perfectly that the same force which keeps the moon in orbit is the same force which pulls the objects down. He realized that the moon was in equilibrium condition with the centrifugal force equal to the gravitational attraction. And this is how Newton formulated his theory of gravity. Another famous thought experiment from Newton was the following. He imagined a cannon on the top of a mountain at the point B. He imagined that if the cannon could shoot a bullet some velocity, the bullet will fall in a parabolic motion. But if the bullet was shooted with enough speed, enough velocity, it will reach some orbit. It will keep in orbit around the Earth. And this is precisely what happened with the moon. The moon is basically in a free fall condition with the gravitational attraction in equilibrium with the centrifugal effect. So, besides that, Newton formulated three laws of motion. The first law is the law of inertia, with the mass being the measure of the inertia, at least for linear motion. For circular motion is the moment of inertia. And then, of course, the inertia offers resistance to the motion, to the change of motion of an object. The second law, he formulated in this way, the sum of forces is equal to the change of momentum in time, change in time of momentum. Normally in the school, in textbooks, they put mass times acceleration, which is not correct actually. What we have to do is derivative with respect to time of the momentum because sometimes even the changes of mass generate effects which can be considered as a force. And finally, the third law is action reaction. It means that for every action there is a reaction. Or, in other words, let's assume that you are standing over the earth. You are executing a force, which is your weight, over the earth, but at the same time, the earth is executing an opposite equivalent force, which is the normal force. So, that's an example. Another example is this balloon, where of course there is a force down uh, executed when the gas goes out, and this is what makes the balloon to goes up. So the third law of motion is the action reaction. Another example, clearer because this one is not so clear, is for example you hit a wall very strong. So you are hitting the wall with some strength, but the wall is also hitting you with the same strength. So this is called action reaction, and it has applications in several fields, including engineering, when they apply static to some mechanism. So in modern physics, we will go now to electricity and magnetism. They were believed to be different manifestations, or let's say better it's better to say they were believed to be different phenomena. But it came out with the time that they are just different manifestations of the same phenomenon, which is electromagnetism. They are related. On the right hand side, you see a electric dipole, positive and negative charges. On the left hand side, you see a magnetic dipole, north and south pole. The difference is clear that while I can separate electric charges into positive and negative clearly, in magnetism, I cannot separate the dipoles. When I cut this magnet in between, I will obtain two magnets, each one with north and south pole. That's clear. So, but how could people realize that electricity and magnetism are manifestations of the same principle? It came out with some experiments with the Biot Savart, thanks to Ampere, Biot Savart, and other guys who realized, for example, that when I put a magnet around a wire involved in this way, when I move the magnet through the through the wire, due to the variation of the flow of the magnetic field, then an electricity is induced here. This is the principle of the generators actually. Generators which bring electricity to our homes. That's a remarkable application of electromagnetism. The other phenomenon is when a current flows, a magnetic field is generated, which rotates around the wire. So in this way, and this example also illustrates the same principle, where the changes in magnetic field can generate currents along the wires. So in this way, it was always suspected that magnetism and electricity, pure electricity, pure magnetism, should be correlated. And thanks to Maxwell, who realized that this is the case, and he formulated his Maxwell equations, which bring out the electromagnetic theory, which obeys the Lorentz symmetry. But as a consequence of the Maxwell theory, electromagnetic waves emerge. Electromagnetic waves which propagate at the speed of light, and they consist of an electric and magnetic field which oscillate in phase with respect to each other. This is a transverse wave moving at the speed of light. Interestingly, the electromagnetic waves they don't require a medium of propagation. They can propagate through the vacuum. And this is the difference with respect to ordinary waves. The applications of the electromagnetic waves are tremendous. They can be applied, for example, in radio signals when the radio stations emit certain frequency of electromagnetic waves. We have our radios at home, and we synchronize the frequency of the radios of our radio with the frequency of the radio station. Then, of course, we can catch the signal, and this is a tremendous application. It's the application to of the radio waves, basically, and this is a manifestation of a phenomenon which is deeper. It's called resonance. Resonance because we need to uh, arrange this internal circuit of our radio such that it generates a resonant effect in order to amplify the signal which is coming from the radio station. Other applications of the electromagnetic waves are X-rays. Of course, the light itself is electromagnetic waves. Uh, and well, in medical applications, we have basically the X-rays, uh, material science when we use the microscopes for X-ray microscopes for analyzing materials, and many other applications. Thanks to the fact that the electromagnetic waves don't require medium of propagation, we can have communication on the space where there is no air, there is no medium of propagation. That's why we can see also the sun, the sunshine, or other and the stars on the sky because the light don't require doesn't require a medium of propagation. That's very important. But then let's summarize. Electricity and magnetism were unified in the electromagnetic theory. So Maxwell theory basically obeyed the Lorentz transformation, and this Lorentz symmetry is what Einstein took for adapting to the dynamic of Newton and then create a special relativity. So in fact, what Einstein realized is that the dynamic of Newton was not right, but instead we have to adapt the Lorentz transformation, which came from Maxwell theory, to the dynamic of Newton for generating a special relativity. How could this idea come out? First, in the past, it was believed that all the waves require a medium of propagation, and they believed that the light was not the exception, and the electromagnetic waves were not the exception. Then they imagined that there was a hypothetical medium of propagation, they call it ether, and through which the light, as well as any electromagnetic wave, should propagate. Then, for measuring the light, the speed of light relative to the ether, they did two measurements, one separated from each other every 6 months. Then, for example, one, uh, we have our planet in this position, so they measure the speed of light in this direction, and they waited 6 months and they measure again. So if there is a medium of propagation, then there must be some differences in the speed of light uh, when they measure every 6 months. This is the famous Michelson-Morley experiment, which was a catastrophic failure. Not catastrophic because it helped us to understand more the physics, but it was the verification that the ether didn't exist as Einstein realized. He realized that the ether was just fiction and it didn't exist. Then what Einstein realized that is that the speed of light is an invariant and that the concept of simultaneity is relative and that the space and time are relative. So in one thought experiment, he realized, for example, you have a thunder light falling on the tree A and B at the same time with respect to the observer C. This observer will perceive naturally these two phenomena as simultaneously. However, the guy who is in the train moving to four-fifths of the speed of light will perceive the event on B first and the event on A after. So this is the concept of relative simultaneity. Einstein then could extend the concept of relative motion. Uh, if you remember a little bit from your Newtonian physics, if somebody moves inside a train with a ball, moving at constant speed, and this ball moves vertically. Let's say the person throws the ball vertically from the frame of reference of this person here on the train. This person will perceive a vertical motion like this. However, the person on land, on solid land, will perceive the same experiment as a parabolic motion. Even if the two motions are in principle different, still both observers will agree on the physics they have to use for describing the motion, because they are separated only by inertial frames of reference. In other words, this train moves at constant speed, so it can be considered as an inertial frame of reference. So special relativity emerged due to the invariance of the speed of light and the relative of space and time, and relative of simultaneity. It's the unification of electromagnetism and the Newtonian dynamics. The speed of light is an invariant, as Einstein realized, and the consequence, space and time are relative, and this was verified experimentally subsequently. One experiment which can be done, but of course, this one is hypothetical, but it can be proved also in the high energy accelerators. Is imagine a rocket moving at a speed near to the speed of light. For that rocket, from the frame of reference of the guy inside the rocket, the distance he has to travel, which initially is L0, is contracted in his direction. Is contracted in agreement with the Lorentz factor due to special relativity, due to the relativity of space. On the other hand, if a person is on the Earth and a person and your twin is on a spaceship, and this spaceship move at a speed near to the speed of light, the clock inside the ship will move much slower than the clock on the Earth. And it's equivalent to say that the person inside the ship is traveling to a future. By the time the person goes, let's say, to Alpha Centauri and come back, will find that you are very old or you are that, either way. So, in other words, this is the example of time dilation due to special relativity, and this is a length contraction due to special relativity. Both phenomena were proved experimentally. And thanks to that, special relativity could explain several observations which were unexplained before. One of the first observations special relativity could explain is the fact that the muons, which are particles with a mass with the same charge of an electron, but much more massive and with a very short lifetime, they are created in the atmosphere due to collisions of particles. They live short time, so when they start to exist, they are expelled in the direction to the Earth. But their lifetime is not enough for reaching the surface of the Earth. However, given the distance and the lifetime, however, it came out that they could reach the surface of the Earth. And the explanation came out because from the perspective of the mu, they perceive a contracted length in their direction. So the mu is created here, for example, and will perceive this mountain, which has originally this dimension, will be perceived by the mu as this mountain here, very short. From our perspective, when we are in our planet, we will suffer the phenomenon of time dilation with respect to the mu. The mu start to travel toward the Earth, and from our perspective, the clock of the mu is moving too slow. So the mu is traveling toward our future, and that's how the mu is able to reach the surface of our planet. So, in other words, special relativity explains this unusual observation of the fact that the mu can really touch the Earth even if their lifetime is too short for doing that. Nuclear energy exists as a consequence of special relativity. Although nuclear effects and nuclear energy was known before special relativity, The calculations and let's say the right calculations were done after the discovery of special relativity because as a consequence of this theory, energy is equal to mass times the speed of light squared. This means that a huge amount of energy can become mass or a small mass can become energy. And this is what happened in the nuclear fission, for example, when the particles decay or the elements decay, they are splitted into different elements. And if we assume the masses of the element after the process of decay is inferior to the original mass. Okay, here the neutron collides here. It makes decay this element into this, but this element is split in other elements. When we assume the mass of the products is smaller to the original mass, what happened with the missed mass? It became energy. And this is the energy which generates the heat in the nuclear reactions. It generates the energy. It generates electricity for the houses. But it also can make damage if it's not controlled. It can become a nuclear bomb, atomic bomb, or so. Nuclear fusion is the opposite. Nuclear fusion is when two elements are joined for creating an element bigger. However, in the process, energy is released, and it's a huge amount of energy. Also, the H bomb, for example, which has fission, and after fusion, uh, also operates under this principle. Nuclear fusion only occurs at high temperatures. It doesn't occur at low temperatures. However, people are in desperation for understanding how to make nuclear fusion at low temperatures because it would signify infinite amount of energy for our houses, for our purposes, for many things. So this is a consequence of a special relativity. A special relativity explains the mass differences between the elements when they decay or when they are fused. Einstein was not happy with the special relativity alone. He wanted to incorporate gravity. So when you include gravity uh, into the theory of special relativity, you obtain general relativity, which is the Einstein theory of gravity. Nowadays, we know that Newtonian theory of gravity is wrong, and that the theory which which generates appropriate results is general relativity. For example, Newtonian gravity cannot predict gravitational waves, cannot explain the precession of Mercury, cannot explain the deviation of the paths of light due to a source. They cannot explain the dragging effect or the black hole's existence. Then general relativity could do all these predictions and they were tested one by one. First of all, general relativity says that gravity is not a force. What happens is that when you have a source, that source deforms the space-time. And then, of course, any particle you put around the source, it can move freely. It can move freely, but it will follow the shape of the space-time. And this is what happened, for example, when the paths of light reach the neighborhood of the sun, they will deviate due to the presence of the sun. And this was the famous Eddington experiment, actually. One of the first evidences of general relativity came through this experiment. You have your telescope in the air, you want to see this star. This is the real location of the star, but the path of light is deviated due to the gravity of the sun and reaches us, and then we believe that the location of the star is here. This discrepancy in positions can be measured when there is an eclipse. And this was measured by Eddington and many other expeditions and was proved to be true, to be right, with the appropriate value given by Einstein theory. Einstein theory has two components. The left-hand side of the Einstein equations is geometrical. It has the Einstein tensor and the cosmological constant term. On the right-hand side, we have the source terms, which is the energy momentum tensor, which contains energy, momentum, flow of momentum, and flow of energy. The Eddington result of the deviation of the path of light is a consequence of the equivalence principle, which suggests the following. Imagine that you're in a rocket in the space and the rocket accelerates 9.8 meters per second squared. This is equivalent to just standing on the air and feeling the gravity of the air, which is 9.8 meters per second squared. So those frames of references will perceive the same, and if you throw an object here, the object will fall to the floor at the same acceleration as it does on the Earth. So in other words, there is no difference between those two experiments up to small deviations due to tidal effects. Another version of the equivalence principle is this: if you are in the space, uh, you don't feel gravity. But on the air, if you are in a free fall, for example, the guys who like to jump in parachutes, when you are in a free fall, you will not feel you will not feel gravity. You will recover the flat space-time of special relativity. This is called uh, equivalence principle. And because of this equivalence principle, precisely that's the reason why the paths of light deviate. Because if you accelerate a rocket and a path of a ray of light enters the rocket, the tendency is the ray will deviate below. And the same has to happen then when there is a gravitational felt. And this is what Einstein thought. He did the calculations, and incredibly, the numbers match with the observations. Remarkable. Other tests and success of general relativity are the following. The prediction of the precession of the perihelion of Mercury, this was a mystery in the observations until Einstein theory came. The orbits of the planets are not ellipses, as Newton said, are they take instead this shape, which is like the precession of an ellipse, no? And this was predicted by general relativity, and thanks to this prediction, they could verify that the anomalous orbit of Mercury was due to the precession. All the planets suffer precession, but in Mercury is more evident. Other success of general relativity is the existence of gravitational waves, which were discovered indirectly by Halls and Taylor in 1974 because they predicted the general relativity predict the rate at which two objects will approach when they orbit around each other, and this rate of approach is proportional to the energy emitted by the gravitational waves. And it came out that in 1974 they could realize that the rate of approach matches with Einstein theory. But people wanted to detect the gravitational waves directly, not indirectly, as Hawes and Taylor did. And this was the success of LIGO. I think was in 2015, the LIGO collaboration discovered the existence of gravitational waves directly with the collision of two black holes. Other experimental success of general relativity is the existence itself of black holes, for sure, that they have been observed in our galaxy. We have one in the center, and there are many black holes everywhere in the universe. Additionally, the Dragon effect, which is the following. When an object rotates, for example, the air rotates, the space-time is a fluid. So it makes the fluid around to move, not to drag. If you do this in water, the water but the same happens with the space-time. The space-time is a fluid and it will be dragged by the motion of the objects. This is more evident in a black hole. The black hole rotates and the dragging effect in the black holes is tremendous. But in our planet, it's very tiny, but it could be measured by NASA by putting a satellite. Um, and after several years, they measure the degree of deviation of the object they put on the space, and they realize that it matches with the theory of gravity. If I am not wrong, this dragging effect has been tested experimentally already. Most likely, yes. The black holes, for sure, they are super tested experimentally. They have been observed. We have the first photography of a black hole, which was taken a few years ago. So there are plenty of evidence of their existence. When we are in the neighborhood of the black hole, the time simply stops. Basically, the person who is next to the black hole will perceive everything in fast motion around, and vice versa. If we see somebody going to the black hole, we will see this person like paralyzed, not moving, because of the difference due to the time dilation, gravitational time dilation, due to the presence of gravity. Gravity made the clocks to run slower. The GPS works very well thanks to special and general relativity. Our satellites, the GPS operate because we have a triangle of satellites in this space. Those satellites they have to move very fast for keeping in orbit. Because they move so fast, they have relativistic effects due to special relativity. So it means that since they move so fast, they are traveling to our future. The clock's much slower with respect to us, and this effect is cumulative. It requires some correction. And in this case, the clocks of the satellites have to be corrected to match our clock. In the same way, but it's a different effect, is that due to the absence of gravity, the time runs faster gravitationally for the satellites. So it's an effect opposite to the motion effect. And they have the tendency to cancel each other. The gravitational time dilation tries to cancel the special relativistic time dilation. However, they don't cancel exactly, and these two effects have to be considered for doing the correction of the clocks of the satellites with respect to our clocks. And that's why you don't get lost when you use the GPS, thanks to these seemingly stupid changes. You can see how useful is physics. Physics is the most useful thing you will see in your life. I cannot see the world without physics. Without physics, the planes cannot fly. Without physics, you will not have a cell phone. You will not be so comfortable in the chair where you are. You will not have refrigerators. You will not have air conditioners or things like that. So physics is extremely important. Please pay attention to that in this class. Please pay attention to physics, learn to love physics, learn to follow physics, and so on. Now, we will finish this first part of the unifications as follows. Electricity and magnetism is electromagnetism. This is the Maxwell theory. Electromagnetism plus Newtonian dynamics is a special relativity. This is the Einstein theory. Special relativity joined to gravity is general relativity. And in the next lecture, we will go with quantum mechanics. So wait for the next video, for the next lecture, where we will start to talk about quantum mechanics and how was that revolution and other unifications which were done during that process. We will be discussing quantum mechanics, the unification of quantum mechanics with special relativity, which is quantum field theory, and subsequent unifications. The unifications not only at this level, but unifications of the four fundamental interactions. Please wait for the next video, and I think I will stop this lesson here.